Welcome back, everybody. In this video, we want to continue on from the previous video. In the previous video, we were able to prove that continuity implies integrability. So we said if we had a continuous function on a closed interval AB, then we knew automatically the function was integrable. So we would like to extend this a little bit. And so let me tell you sort of the philosophy we're going to follow, kind of the story, and then you'll see why we're going to prove this one particular theorem in this video. So if I have an interval AB, and again, we know if we knew f was continuous everywhere on the interval, then we know the function is integrable. But what if we had some points of discontinuity, right? Let's say we had, I don't know, maybe 4 points of discontinuity. What could we do then? So what we want to do is we want to break up the interval so that we can always put these discontinuities on an end. So I can break it up right here, and I can break it up right here, and break it up right here, and break it up right here. Okay, and I want to know, well, okay, what if I just integrate over, say, this first little piece, right? Or maybe on this little piece, or this little piece, or this little piece, where I have some sort of a discontinuity on an end, right? Is that going to cause any sort of a problem, right? And so in order for us to analyze this question, we need to know what happens if you try to integrate over a subinterval, right? Say I knew that a function was integrable on the entire interval AB, what would happen if I integrated on a subinterval? Or going the other way, what if I knew I could integrate on any of these subintervals? Could that imply that I can integrate over the entire interval? So that'll actually be the content of the theorem that we prove in this video. All right, so our theorem, which is that, well, how we integrate across a divided interval. So I'm going to start with a bounded function on a closed interval. Okay, and then I'm going to take some point in between A and B, so it's not going to be on an endpoint. So C will be in the open interval AB. The claim is that f is integrable on the entire interval AB if and only if f is integrable on the subinterval AC and on the subinterval CB. So the picture now is a little bit simpler. I break up the interval at one point. That's my C. So I have A and I have B. And so I'm just going to check these two. And if it works for these two, then it works for the entire interval. And of course, this is really enough for you to break it up over the picture above. Because if I can break it up at one point, then I can break it up at 2 because, okay, let's say I added another discontinuity at maybe at some D here, and I want to break it up. Well, I can first break it up from A to C and then from C to B. And then this C to B, again, there's just now one point in the middle. I can break it up at that point D. So essentially, we would argue by induction that this is going to extend to not just 2 subintervals, but to any finite number of subintervals. Okay, so by induction, this theorem extends to any finite number of subintervals. Okay. There's another little bit to this theorem, though. Not only if we know integrability on the whole, do we get it for the parts, or on the parts, do we get it for the whole? But we even know a relationship between the integral values. So this is something you probably remember from your Calc 1 or Calc 2 course. Well, let's make this clear. So in this case, we have that if I integrate f from a to b, I get the same thing as if I integrated from a to c and added the result for when I integrated from c to b. So this will be helpful. Okay, so in class first time through, we did not prove this, but you know what? Let's give a proof here. All right, this is actually going to be a reasonably challenging proof, or at least at the very least, it's going to be a long one. So first, we want to show f is integrable if and only if it's integrable on the sub pieces, right? So let's assume f is integrable on the entire interval. All right, well, by the integrability criterion, we know that there exists some positive k such that for all epsilon greater than 0, there exists a partition. And I'm going to be very explicit about what this partition looks like. So as usual, we can have an x0 and an x1 and so forth. However, I want to put this c, right? This c where we're breaking the interval up in here. And maybe when I use the integrability criterion, the first time I do it, the partition I get doesn't involve c. But if I include an extra point into a partition, the difference between the upper and lower sums only gets smaller. So it's okay to refine a partition. It's not going to hurt anything. So let's say that the nth term is equal to c. And then I can keep going. Okay, and so this is a partition of the interval AB. Okay, such that, well, I don't want to just pick any partition. I want one for which the difference of the upper and lower sums is less than k times epsilon. Okay, now just a quick observation. When I write down this upper minus lower sum, there's kind of a nice factored form of this. So instead of writing two sums, I can combine them into one sum. And I can write this here as the supremum of f of ik. So I'm going to use this, our usual notation here. Ik would be the interval from xk minus 1 to xk. So I can take the difference of the suprema and the infima for each k, and then I multiply that difference by the length of ik. Okay, so it's important. And an important piece here is, well, okay, we know the supremum is always at least as big as the infimum. The length is always non-zero. So this summand is at least 0, right? Every single one of these is at least 0. So if I add more, I'm going to get something that's, well, certainly no smaller and probably bigger. And if I take stuff away, I'm probably going to be getting smaller. Okay? So that's going to be essential to what we do next. So let's define a new partition. I'm going to call it x less than or equal to c. And this is just going to be the same partition, but I'm just going to cut it at c. And also let's define a greater than or equal to c version of x, which starts at c and ends up at xn. So I'm essentially chopping this original partition x into two pieces, right, at c. And so if I do that, I can compute the upper sum for, say, x less than or equal to c, and then subtract the lower sum. And the point is when I do this, I'm getting rid of all of the partitions right after c. So I'm getting rid of a whole bunch of non-negative terms, which means that sum is going to get smaller. So this will be less than or equal to the difference of the upper sum over all of x and the lower sum over all of x. But this difference was less than k epsilon. So I've now gotten this difference on this smaller partition to be less than k epsilon. And the same thing works if I'm using, of course, the upper, the greater than or equal to version. So that will also be less than UF of x minus LF of x, because again, you're removing non-negative terms. And so already by the integrability criterion, we conclude that f is integrable on the intervals, well, remember this x naught, right? That's equal to a. So this is, we're going to have an integrability on AC, and then this xn is equal to b. So we have integrability on CB. So by the integrability criterion, f is integrable on AC and CB. Okay, so that's one direction. Okay, let's do the other direction. Here, we'll switch up colors for us now. All right, so conversely, well, now we're going to assume that f is integrable on AC and CB, which again, we can use the integrability criterion. And so now we're using it individually on these two pieces. So I got to do everything kind of special, separate for these. So there's going to exist two constants. Let's call them L and M now, such that for all epsilon greater than 0, there's going to exist a partition, let's call it U, and that'll be an AC partition. And there'll be a partition, I don't know, let's call it V, which will be a CB partition, such that if I take the upper sum for U minus the lower sum for U, this can be less than, let's say, L epsilon. And we got to do the same thing for V. So UF of V minus LF of V is less than now M epsilon. Okay, so what I want to do now is build a partition for the entire interval AB. And the way I'm going to do that is by, well, it's essentially abusing some notation. So let's define, let's call it Z, but using our old join notation, right, or wedge notation. Right, I'm just going to put the U and the V together, right? They meet up at the C. So if we were going to try to write this down, right? Okay, so we know that U0 would start at A, and then we'd have a U1 and so forth. And then at the very end, you'd get a UM, which is our C. But then we just continue on. After C, well, C is actually equal to V0. So then you get a V1 and so forth, and you stop at, I don't know, Vn. Okay, so that's how we're going to combine two partitions on adjacent intervals. Okay, so we get this now, this Z, which is a partition of AB, right? Because it's Vn, right? Of course, that's still equal to B. All right, well, what happens when we compute the difference of the upper and lower sums? Well, if I want to compute the upper sum for Z, I'm computing it across, well, first just the U bit and then across the V bit. So in fact, this would be equal to the upper sum over U plus the upper sum over V minus, okay, now I do the lower sum over U plus the lower sum over V. Okay, and that's just because how would you add up all these things? Well, you add up the first M of them, and then you add up the next N of them, whatever. Okay. Okay, but I can rearrange this. So this is equal to UFU minus LFU plus, then I have UFV minus LFV. But I have estimates on those. So this is going to be less than L epsilon plus M epsilon, which is L plus M times epsilon. And of course, L plus M is positive. Hey, there we go. By the integrability criterion, we're done because we've just shown the difference of the upper and lower sum on some partition is less than some positive multiple of epsilon, right? And this positive multiple does not depend on epsilon. So by the integrability criterion, f is integrable on the entire interval AB. Okay, so there was something else though, right? What was that? Let's see, let's go back up. F is integrable on the entire interval, if and only if it's integrable on AC and CB. Yep, we did that. Yes, right, the relationship between the actual values of the integrals, right? It's supposed to be that you just, okay, add up the integrals on the subintervals, and that'll give you the integral on the entire interval. All right, so the way we're going to do this is, I don't know, it's kind of weird. You can see this is a really strange way to prove two things are equal. So we're going to keep all the notation that we had in the first half of the proof. Okay, so this X will be a partition for AB. We have the less than or equal to if we need that, blah, blah, blah. Okay, so here we go. So now let's let epsilon be greater than 0. Wait, why? We're trying to show two things are equal. Well, we're using this trick again where we want to show two things are equal by showing that they're less than epsilon, or in this case, some positive multiple of epsilon for all epsilon greater than 0, right? K here is some positive constant. All right, so it's actually going to be even, I mean, it's even going to be a little wilder than that, right? It's going to be really crazy. Okay, so check this out. Let's start with the integral of f over ab. So we know that this is less than or equal to what you would get if you just took an upper sum over some partition x, right? The partition we had in the first part of the proof, right? Because we know that these upper sums are always sort of two big approximations, right? They're always upper approximations. Okay, but we know that the upper sum of this x, right? Let's head back up here to the green. The upper sum of this x minus the lower sum is less than k epsilon. So if I just have the upper sum, I can add the lower sum to both sides. And I will get that this is less than the lower sum plus k epsilon. Okay. But as we were seeing in the last part of the previous part of the proof, if I wanted to compute a lower sum over, say, the entire interval AB, that'll actually just be the sum of, well, I just break up the lower sum into two pieces, right? The two subintervals that bring it together. So what I can do is rewrite this LF of x as LF of x less than or equal to c. So I do all the stuff to the left of c, plus the lower sum on x greater than or equal to c. And then I still have plus k epsilon. Okay, but these lower sums are each less than or equal to the corresponding integral for f, because heck, lower sums are lower estimates. So in this case, since we're just doing the lower sum over the partition which goes up to c, this will be less than or equal to the integral from a to c f dx. And this one here will be less than or equal to the integral starting from c and going all the way to b. Aha! Hey, that's pretty good. We've got our integral that we wanted and the integrals that or that we started with, and we got the integrals we wanted, and well, all we see so far is that one is less than or equal to the other. But let's keep going, right? So this integral is less than or equal to if I did an upper sum. So if I do an upper sum over less than or equal to c, that will be, again, it's an upper estimate for this integral. And the same thing if I do the upper sum for x greater than or equal to c. That'll be an upper estimate for this integral. And again, I still have this k epsilon. Okay, but once again, we know that the upper sum of, say, x less than or equal to c minus the lower sum is less than k epsilon. I again can add the lower sum to both sides. And so this upper sum is actually going to be less than the lower sum less than or equal to c plus k epsilon. And then the second one will be less than the lower sum of x greater than or equal to c plus k epsilon. And then you still have a k epsilon. Okay, but we can put this all together now. I have a lower sum for x less than or equal to c, the lower sum for x greater than or equal to c. I put those back together as the lower sum of x. And then I have 1, 2, 3 k epsilons. Okay, but now this lower sum is less than or equal to the integral, because lower sums are always lower estimates, right? Okay, so now I started with the integral of f over ab, and I finished with the integral of f over ab, but there's this 3k epsilon. But remember, this is true, right, for all epsilon greater than 0, which means that the difference between these things, right, okay, 0, which they should be, right, like we actually know these are equal, right? And this is, of course, just verifying what we saw, right? Okay, because they just differ by some, well, in this case, multiple of epsilon. That's fine. But when you have a sequence of inequalities like we have, and you start with something and you end with something, and they're all equal, right? The beginning and the end here are equal, then everything in between has to be equal, at least when you remove these epsilons. Okay? And so what are the key ones that we want? Well, we have this one here, and we have this one here. So everything in this list has to be equal when you remove the epsilons. And so from here we can therefore imply that the integral of f from a to b is the integral of f from a to c plus the integral of f from c to b. Whew, that's a tough one. That's a weird one, isn't it? Okay, so what do we want to do with this? Well, what we're going to prove in the next video is that as long as we have discontinuities like this, it's just like a discontinuity, and otherwise we are nice and continuous, right? Or even just integrable all the way up to this discontinuity, then we're still going to get integrability even when we include this discontinuity on an endpoint. And using this theorem, well, okay, we can just keep breaking things up so that all the discontinuities are on the endpoint, at least as long as there's a finite number. But this is going to allow us to prove that whenever you have a function with just a finite number of discontinuities, it will still be integrable. Okay, we will see you next time as we continue our journey.